let me introduce Martin, who's a very old friend, actually, as well as a colleague. As you've read, I think, in the registration process, he was an undergraduate in physics and chemistry, class of 72. I don't know why he left MIT, but he went to Berkeley and got his PhD there. But then he came back. He saw the mistake he had made and came back to MIT. And he's worked for over 40 years as a research scientist with me, actually, at the MIT Plasma Science and Fusion Center, working mainly on fusion energy development. I say mainly because he has a lot of other talents as well, particularly in the IT area, which he is very important in our overall program there. He's also well known in the world of fusion science. He's as the discoverer of the so-called Greenwald density limit. I hope he's not going to explain that to you tonight. No, he won't. Yeah, a little complicated. But anyway, he is very well known. And importantly for tonight's talk, in 2018, he co-founded a private enterprise called Commonwealth Fusion Systems, which is a spin-off really from MIT. And they are building a facility in Devens. Maybe some of you know it as Fort Devens, but they dropped the fort now because it's just Devens. And that's where they're building this new facility. And I think you'll probably tell us a little about that. Or yes, are you going to build? You're going to talk about a little about? Yeah, I haven't seen this talk. Picture or two, so we'll find out. So without further ado, I do want to introduce Martin and thank him for coming and look forward to his talk.
All right. Yeah. So let me thank them for their invitation, and to thank Ron, really for my whole career. I have to say, he hired me about 45 years ago, and we really, and it was a great group. We had a lot of fun, and we even made a little history. So it was really a great experience, and so I have to thank him for that. Okay, so I'm going to talk a little bit about fusion and our approach. Of course, a lot of people contributed to this work, but really we come in two flavors. There's a group at MIT and a group at Commonwealth Fusion Systems, which is our spinoff. And originally the MIT group was about 10 times bigger than the Commonwealth group, and now they're easily 10 times bigger than we are. So it's been I guess a success as a business. So I'll give you a brief introduction to fusion energy. And then I'll say a few words about inertial fusion, mainly because this was in the news, and they made a very notable achievement in the last month, and I want to put that into perspective. But most of this is going to be about magnetic fusion, our use of high temperature superconductors, and what are our plans and projections going forward. So I think we all can agree the world needs carbon-free energy and clean energy. I mean, it's, of course, global warming is an issue, but all sorts of pollution are a problem. So that's a big planetary-wide problem. For people like me, the question is fusion going to contribute to the solution? And we've been working on it for a very long time. We think we can contribute, but that's the challenge to us, to actually be relevant to this very serious problem. Just a little background. So fusion is the process where light elements combine to make heavier ones and release a huge amount of energy. It's the process that powers the stars and creates all the elements of the periodic table. And here you can see the very famous curve of binding energy. The most stable atom is iron. Heavier atoms like uranium can be torn apart to release energy. That's fission. We're talking about the other side of the periodic table, where very light elements, in our case, isotopes of hydrogen, combine to make helium and also release a huge amount of energy. There's an interesting historical point here. the idea of using fusion for practical energy goes back a little over 100 years now to this guy, Arthur Eddington, a really bright guy who in 1920, he noticed that so the problem was this. The sun was obviously burning very hot, sitting up there in the sky. And that was okay when you thought the Earth was fairly young. But geologists showed in the 19th century that the Earth was at least hundreds of millions of years old, if not older. And there was no process known that could keep something that hot that long, even though it's very large. So it was a mystery, one of the big mysteries of science in the 19th century and before. He noted that the mass of 4 hydrogen nuclei was a little bit less, actually, I should say that wrong, a little bit more than the mass of helium nuclei. This was just measured by a chemist whose name I forget. And he speculated, okay, there's a process. No nuclear physics was known at the time. They didn't know what a neutron was. They didn't know really what a proton was. But they said, look, he said, look, this is probably where it comes from by a process we don't know. He did know about E = mc squared, which, he's post-Einstein, and proposed that's where the sun's energy came from, and noted here in this quote below that we could probably figure out how to use this on Earth to supply energy. And even, he says, or suicide. He sort of foresaw that this could be used as a weapon as well. It's an amazingly prescient guy. It turns out that all the sources of energy that we use, if you look back far enough, come from fusion. The sun, of course, directly, can be used to convert to electricity with solar panels. Through photosynthesis, it makes biomass. You can burn wood. Then we learned how to burn fossilized versions of wood, coal and oil. Of course, the sun drives all the weather. So the wind, hydropower, it comes from the water cycle driven by the sun's energy. And even exotic things like geothermal, nuclear fission, eventually come back to fusion that occurred in this case, supernovas, and made the heavier elements in the periodic table. So that's really the source of energy in the universe. On the sun, the cycles are not the same ones we would use here on Earth. There's a proton-proton chain. There's a carbon-nitrogen-oxygen cycle for fusion, but those are very, very slow reactions, which is a good thing. I mean, the sun has been burning for 5-10 billion years, and we think it's going to burn for another 10 billion years. If it burned out quickly, we would be in a lot of trouble. So that's good, but that's not practical on Earth. So on Earth, we need a faster process. So we use a higher test fuel. We go to higher temperatures and we use a high test fuel that is deuterium and tritium. One of the challenges is, of course, that while deuterium is plentiful, it's about 1 in 6,000 or 7,000 atoms of hydrogen are made of deuterium, a heavier isotope of hydrogen. Tritium really doesn't exist. It's an unstable element, so there's not much of it around. So we have to make our own. So what you see there is in that red square rectangle, that's the process that occurs inside the plasma. Deuterium and tritium fuse, they make helium. The helium is retained inside the plasma and it keeps the plasma hot. The neutron, because it's not charged, is lost from the plasma. We capture it in what we call a blanket, and there's a breeding reaction between the neutron and lithium that makes the tritium that we're going to need and another helium atom. So the net reaction shown at the bottom, the fuels we use are deuterium and lithium. We get out helium and a lot of energy. The tritium and the neutron are recycled within the plant. So they're not really fuels, they're sort of intermediate things. Now, once you get that to work, the electricity that you make is just by conventional steam. It's a firebox, except it uses fusion instead of burning coal or oil or something like that. So one of the advantages of fusion is that it can fit into the footprint of existing fossil fuel plants. Now, the fuel is extremely energy dense. I have some numbers here where you compare typical fossil fuels, tens of kilojoules per gram. You go up to nuclear fission, you're 1 million times higher. You get to fusion, now you're 10 million times higher fuel density. And, the result of that is that if I took 28 grams, that is 1 ounce of lithium deuteride, you could carry it around and hardly notice it, put that in a fusion machine, it would provide all the electrical energy used by an average American in their entire lifetime. And that's just not the energy you use in your house. That's everything that's made in your name, by industry and, the light, keeping the lights on in the business that you work in and the grocery store. It's all the electricity that you're responsible for consuming directly or indirectly. So that's amazing. So there's essentially an unlimited amount of fuel. So what are the advantages? Well, of course, I already said that there's abundant high energy density fuel, no greenhouse gases, no particulates, no nitrogen oxide or sulfur dioxide. So clean in that sense. Well, if you compare it to fission, it's not a chain reaction. So there's no or very minimal after heat, much less residual radioactivity or waste. To the point where nuclear regulatory agencies have said, control of a fusion reaction is not a safety issue. Cooling is not a safety issue. And if you know about fission, those are two of the big challenges for safety. And I'll mention this later, but we are working on a new regime to particularly license fusion versus fission plants. There's also minimal nuclear proliferation risks, which is another thing you worry about with nuclear fission. Compared to renewables, the advantages it has is, there's minimal land and water use. It doesn't require major modification of the electrical grid. These are all challenges for renewables, and it's on all the time. You don't have day and night. You don't have seasonal changes. So it has all those advantages, and then the cons, and there must not be very many because I didn't leave much room. And the one is that we don't really quite know how to do it yet. We're getting very close, and I'll try to get where we're actually getting. We're almost having challenge. There are a lot of technical challenges, but in a way, they kind of originate in the fact that fusion is mediated by the strong nuclear force, which has a very, very short range, 10 to the 15 meters. And whether you're a technical person or not, you can recognize that that's a very small distance. The nuclei are charged, so they don't want to get that close together. So you have to get them up to very high energies to get them to fuse. And so you can see on the chart on the right, the fusion, this is the cross section, which is just the probability of fusing. Doesn't get substantial until you get up to about 100 keV. If that were a temperature, that would be 1 billion degrees. So very high temperatures required. At those kind of temperatures, matter is in the form of a plasma. I think probably a term most people have heard. It's the fourth state of matter. You start with a solid, you add heat to it, it'll turn into a liquid. The molecules can move around, but they're still dense. A little more heat, and it'll turn to a gas. Now they're really free to move around, and there's lots of space between them. Some more energy, and you pull the electrons out of the atoms, and now you have a charged gas, a gas made of charged particles, and that's a plasma. Most of the visible universe is in the form of a plasma. So the supernova remnant, the Crab Nebula, is one example, but also lightning auroras, neon signs. Those are all examples of plasmas. We're kind of unusual as people to not be made out of plasma. Most things in the universe are. So getting back to this case again, I can show you here that while the fusion reaction is peaked, it's never as large as the probability of just scattering. And what that means is that a given nuclei in one of our plasmas is going to collide many times before it fuses. So it thermalizes, it isotropizes, it becomes a thermal plasma, not just a fast particle. So you can't make fusion energy with beams. You can demonstrate fusion that way, but you can't make net energy. So you have to heat matter to the point where it's a plasma and then insulate it and isolate it from ordinary matter until it fuses. And that's the challenge. We've known what it takes for a long time. This is a document which is almost 70 years old, declassified, has the declassification stamp on it. So I won't go to jail for showing it to you. The program was actually declassified in 1957, but this guy, John Lawson, basically did the algebra to figure out what would be required back in 1955. And we have been trying to achieve that ever since. One of the experiments that Ron and I worked on came very close in certain parameters to this, but nobody's put it all together. So what does it take? Again, not to worry about the details and the numbers, but you need enough fuel density, a high enough temperature, and you have to have good enough insulation, holding the heat long enough. Those three things are required to make fusion work. And we have a metric. It's not an exact metric, but it's a nice scalar rule of thumb about where you need to get to in a plasma in order to get fusion. So we know what our target is. How do we do it? Well, there's three ways you can control fusion. One is by gravitational confinement. You have this deep gravitational well in a star, in the core of a star, and even the very fast particles are trapped. And the confinement's amazing. The energy that's released in the sun takes 1 million years to get out for us to see it. And the burn-up time is really slow, like 10 to the 10th years. So this is a really slow process, very low energy density. Your body produces, your metabolism produces heat at a higher volumetric density than the sun, but it's big. The second way is inertial confinement, and that's not really confinement at all. You just implode some fuel and it heats and it gets dense and it releases its fusion energy, in this case in 100 picoseconds, before it has a chance to fly apart. This was the principle that underlies the H-bomb and also the experiments at Livermore that you've probably read about. What I'll mostly be talking about is magnetic confinement. That's kind of like in the Goldilocks and the Three Bears story. It's like the just right. It's not the lowest density, lowest power density, slowest, not the highest power density, fastest. It's in between. There we use magnetic fields to confine the plasma. So let me just say a few words about this because, again, it's been in the news. And there was a really significant historic achievement here. We've been trying to reach this Lawson criteria for 70 years now. This was the experiment that was the first to get across the line. And they use very, very powerful lasers to compress and heat a tiny capsule of fusion fuel and therefore make it work. You can see from the pictures that you have sort of a tin can, you impinge lasers on the inside of the can. That creates X-rays. The X-rays implode the capsule, and when it gets tiny enough, it will begin to fuse. And the facility is huge. You can get some idea. This is the target chamber. Here's a person, so the target chamber is a lot bigger than a person, and there's the target chamber within the facility. So just an enormous facility. It's an impressive thing to see, and the hardware is amazing. So that little target here, this you can see if you look at the middle picture, you can see how small the tin can is, and realize that lasers then that fill 3 football fields, that's the power of those lasers is all focused on that tiny fraction of a millimeter. It's an amazing feat. Well, what does it mean? I mean, so again, it's a technical tour de force. It's an historic achievement. They do some really important science. But what about energy? Well, so speaking for myself, I have my doubts that this will be a practical energy source. The extrapolations that are required are enormous. You need to get the gain of another factor of 100 higher. The repetition rate has to go up by about 1 million. The laser efficiency needs to go up, improve by 10 to 100. The capsule costs have to go down by about 100,000. So these are all big numbers. They have a story to tell. They're convinced it's going to work. It's funded research. They're going to work on it, and time will tell whether they're successful. But meanwhile, we're working on a different scheme. We use magnetic. And the basic process is actually pretty simple in the sense that if you put a charged particle in a magnetic field, its motion is curved, bent by the magnetic field. And the orbit it follows are these helical orbits where they circle around the magnetic field lines. The more energetic they are, the bigger the orbit, the heavier they are, the bigger the orbits. And the stronger the magnetic field, the smaller the orbits. And that's really important for our story. So for a field of about 10 Tesla, and that's the order that we're talking about, that's 20,000 times the Earth's field. So it's a pretty high field magnet. And average temperatures of 10 keV, that's 100 million degrees. The ion gyre radius is 1.5 millimeters. And the physics says that you need a device that's 500 to 1,000 gyre radii across to make that work. So for these conditions, that's 1 meter. So you need a plasma with a radius of about 1 meter, that says, to do this. If the field's lower, it's got to be bigger. If the field is higher, it can be a little smaller. Now, of course, that doesn't confine the particles along the field lines. They're free to stream. And at the temperatures we're talking about, those ions are moving at 1,000 kilometers per second. And even at those temperatures, the average time for an ion to fuse is about 25 seconds. So that really doesn't just have a long solenoid. It would have to, be close to the size of the circumference of the Earth to work. So for a practical device, you have to get rid of the end losses, eliminate the end losses, and we do that by eliminating the ends. You wrap the field lines around into a torus, and if you see pictures of plasmas or plasma experiments, fusion experiments, you'll always see this donut-shaped topology. In fact, there's a basic theory in mathematics and topology which says if you're going to confine an ion in a magnetic field, the topology has to be a torus. I don't think people knew that when they started this, but somebody came along and said, oh yeah, of course, here's the theorem. One particular configuration works best. It's called a tokamak, actually a Russian invention, Sakharov, if you know the name. He worked on the H-bomb for the Soviet Union, later won a Nobel Peace Prize for his work as a doctor. He was the inventor of this idea. And we've made a significant amount of fusion power. The graph on the right, again, too small to read, but to get powers up to 10 megawatts, 15 megawatts of fusion power. So significant amount of power for short periods of time, but not as much as it took to make that. Well, how well have we done? Here's some, again, using that triple product metric, that graph shows how we've done over time. We've built a lot of machines. I think something like 160 of these experiments, most of them pretty small, but some of them significant. And, as we learned how to do it better and we made the machines bigger, more powerful, we actually exceeded Moore's law for about 30 years in terms of the fusion output. But you can see that it sort of stopped around 1990, early 1990s, mid 1990s. And we want to take the next step. The biggest program to do that is called ITER. It's a joint program of really the entire industrial world. Ron worked on it directly. He was, I guess, employed by ITER at some point. We all worked on it indirectly, doing research to try to figure out how to design the machine, make it work. And it's big. It's probably the largest, most expensive terrestrial scientific facility ever built. Again, another impressive terrestrial, impressive technical tour de force. But that slowdown in progress that I showed is really due to the fact that these machines get very big, very expensive. They take these large collaborations to build, and therefore they're slow. So here's sort of a timeline. The two machines on the left, JET in Europe is just shutting down now. A new machine in Japan is coming up. Not quite sure of its status, but it's been commissioned. ITER is under construction. Exactly when it'll start is hard to know. Research was scheduled to begin in 2030. It looks like it'll be delayed somewhat with the fusion experiment starting in 2035. The US has a plan to follow on to that. The Europeans have a different plan. Their machine's so big, like it doesn't even fit on the view graph. And that time scale is slow for considering the challenge of global warming. And that's not me saying that. That's the IPCC, the International Panel on Climate Change, who says if we want to avoid a real disaster, we've got to get to zero emission by 2060. And so they've gone back and they say, okay, if there's new technology, it's got to first come online in the early 2030s and being deployed at the rate of 10 per year, say in 2040. And then following trends and assuming that there's sufficient interest and investment, perhaps it could be a contributor to the 2060 goal. So obviously the timeline we're on is not going to make that. Well, what can we do about it? So one way to look at this problem is one of these quad graphs. I think people have seen them. So on the vertical axis, we have how much confidence do we have in the science. So if you have a high confidence, you get high up on that graph, and if you have low confidence, you go low on the graph. The other axis, the x-axis here, is how fast, how inexpensive it is. Well, we want things to be small, cheap, fast. Sometimes they have to be big and expensive. So that's another way of ranking how you do. I mean, anybody who's seen these quad graphs know you always want to be in the upper right corner. So there's not a lot of drama here where I'm headed. There is another approach, compared to say ITER. There's a lot of private companies that had invested in alternate concepts, other ideas. They're small enough so they could be carried out with private funding. They could be built quickly, but the physics is really unknown, either unknown or really questionable in some cases. Well, where do they sit on this? Well, you can see that their performance is in that blue square roughly over there on the left-hand graph. So they're struggling to be relevant. They have ideas, but not clear that they can get to where they need to get. So we'll put them on the lower right. They're small and they're fast to build, but we don't have very high confidence that they'll work. So we want to be up in the right corner where the breakthroughs are. And we thought that the way you do that is you combine the known physics of approach like ITER, and you combine that with sort of the agility you might have with something that's privately funded, which is a little more experimental. Well, you still need some technology, and we think the technology that is the basis for that breakthrough is here, not invented within our program, but discovered in 1986. That's a long time ago now. A Nobel Prize was awarded for that in 1987. That was the shortest time between a discovery and a Nobel Prize ever. It was something of a surprise. I mean, they were looking for better superconducting materials. They had no idea they would be this big jump. What I have plotted on the left is the critical temperature versus the year of discovery. And you can see it gradually goes up, and all of a sudden there's a change, and just this spike, and that's the discovery of high temperature superconductors. So great, it made a big splash in the world of science, but was it ever going to be practical? I mean, those materials were in the form of basically black powder, little tiny black crystals. How are you going to make an engineering material out of that? Nobody really knew. Well, some of our guys at MIT, they didn't know how to do that either, but they said, if we can ever make this into a magnet, it's great for fusion. So this actually, if you look there, received April 4th, 1987. This was less than a year after the discovery. They published this paper. And these are old friends of ours who basically said, well, this would be a great idea if we can make the magnets out of that new material. It took some of us a longer time to come around to appreciating that. But meanwhile, these high temperature superconductings, they're emerging from the lab and into some degree of industrial maturity. And there's this boutique industry of making those things. And what they did is they used the same technologies as you might use in making solar cells or semiconductors, thin film deposition. In this case, though, the deposition is on some high strength steel, and you essentially make a huge crystal, a crystal which is a few millimeters wide by a kilometer long. And so you get the advantage of this crystalline form, but now it's in this long tape or ribbon. You can see on the lower left what that stuff looks like. It's just this thin ribbon that if you cool it down below liquid nitrogen temperatures is a superconductor. And it's as close to a miraculous material as you have, which is that it passes electricity with no losses at all. It's really seems like something that shouldn't happen, but it does. And the capabilities of those magnets are increasing. These are just some examples up through 21. On the right's a magnet. We were at MIT, the group collaborated with some other groups to make. You can see MIT's logo on some of those things. The MIT lab that we're affiliated with did some of the pioneering work here. So why do we care for fusion? Well, I sort of hinted at that. At higher fields, the fusion reactors can be smaller, and that's because the way you talk about the size of a fusion machine is really in the number of gyroradii. It needs to be 500 to 1,000 gyroradii. And the temperature has to be 200 million degrees. So how do you get a lot of them? You either make the machine really big or you make the field really high. You can trade those two off, one against the other. So the curve on the right tells you those are curves of fusion gain, the contours of fusion gain versus the size and the magnetic field. And the general shape, of course, we know, that's a real simple calculation. We kind of knew that it would take that form. The precise shape, and more importantly, the labels on those took decades and decades of research to say, okay, where is one going to be on this curve? We knew that they would have that shape, but it just tells you that you can trade off size and field. And that was really pioneered using a series of machines at MIT that used copper magnets. This is the project that Ron and I worked on for years and years. These three machines that were high field copper machines, and basically proved that that principle works. In fact, the US and the world were thinking about building a follow-on that would take this to the next step, but decided to build ITER instead. And the really reason for that is that practical fusion needs superconducting magnets. The copper magnets were great for an experiment, but they take too much electricity. So making net power is not very practical if you don't have superconductors. And the problem is that the best superconductors available basically don't allow you to go above 5 or 6 Tesla in the fusion machine. So that right-hand side of that curve is inaccessible. So ITER, which is this enormous device, is actually as small as it can be, and meet its mission. And its specification was to run at the highest field possible with the technology that was available, which was niobium tin, which is a pretty adventurous material to use for big magnets like that at the time. That itself was by no means a sure thing. It took a lot of R&D to get that. So that set the size, but also, the resources required and the time required. The decision to go ahead with the ITER was made in 1985 at a summit between Gorbachev and Ronald Reagan. And again, it won't be in DT operation for 2035. So something like 50 years and the resources of the entire industrial world. So that's a pretty big project. But with new magnet technology, that restriction is gone. You can slide down the curve and have higher field, smaller devices. And here's an example. This was actually a student project, a graduate student class, to design a machine that would produce the same amount of power as ITER, but using high temperature superconductor. And those are to scale. And you can see that the ARC device on the right is considerably smaller. Well, we really, as a practical matter, we weren't ready for that yet. It would have been if the resources were available and the technology was very, very available, that would be great. But nobody was going to give us the money to take that step. So we said, let's just go a little bit further and demonstrate the principles on a smaller scale yet, and that's the Spark device. And these are to scale. So they all produce comparable amounts of fusion power and comparable performance, but obviously very different scales because the magnetic fields are different. So what's our mission? Our mission is to robustly demonstrate fusion gain, which we defined as Q greater than 2. So Q greater than 1 is, of course, a net power out of the plasma. We aim to make sure that we weren't even close. So we're aiming for 2. The device is capable actually of a gain of 10, we think. So this would sort of be a Kitty Hawk moment for fusion. It's not a 747 flying around a 787, but it tells you can fly. And our hypothesis is that this would be sufficient to put fusion firmly into the national energy plans and attract the investment you needed next. And so far, that hypothesis has been borne out. We also needed to demonstrate the magnet technology at scale, integrated into a device, and to sort of complete the physics basis for this pathway. Okay, that's the aspiration. So what's the plan? Well, first of all, privately funded. We talked to the government. They said, that's very nice, but we're doing something else. So, okay. So we went off, got private investment, spun out a private company. And the goal here was to bolster our own research and education efforts at MIT while building this strong industrial entity. And that's Commonwealth Fusion Systems. The combined team now is 60 people, as I mentioned. Originally, it was roughly, we had at MIT roughly 10 times the number of people as CFS. Now CFS has 10 times as much as our group. So they've grown by a factor. That's an interesting. Is that a home run at? Okay, I'll get there. The first phase was to demonstrate the magnet technology. We did that at the end of 21, beginning of 22. Phase 2, which we've begun, that's the construction and operation of the device. If that's successful, phase 3, CFS would go off and build the first fusion pilot plant. So these are the 6 of us, the co-founders. It's part of an ecosystem of private fusion. It kind of serves as a indicator of the value proposition of fusion. The investors saw fusion as an arbitrage opportunity that, it was undervalued by the government, that the value of a new power source was, and the probability of success were high enough. Interesting to talk to these people who think that way. And we have a lot of players now. So, fusion, we think, is too important to have just one team working on that. Yeah. So we're hoping to demonstrate net plasma gain in 2026, and then in the early 2030s, the first pilot plant. It's very audacious. Yeah, 2026. Yeah. And this is really how technology gets to market. We're kind of following a well-worn path. SpaceX, computers, robotics, aerospace, spinning out science out of universities and national labs. It's going to be how fusion gets to the grid, especially in the US. The US doesn't build power plants. But the government will still have a role doing basic research, supporting the industry, and of course, the workforce development through education. So where are we, right? The team started with 6, is now 600. We've got, okay. We've gotten $2 billion in investment so far, a little over $2 billion. Really surprised me. I didn't think we would have this kind of money in this amount of time, but we do. We've been through a successful conceptual design review. We're moving toward the preliminary design review. Tested a model coil in 21, and there's a bunch of other R&D projects that are moving briskly. We've secured the most critical materials, namely the HTS, the high temperature superconducting tape, and the tritium that we need. The site was purchased and construction began. The manufacturing and office building were occupied just at the beginning of this year. Tokamak building is nearing completion, and major procurements are underway. And the permitting process, which is, of course, an important issue, is well in hand. That's with the state and local government, but we're working with the NRC for a new regulatory regime, and that is also going well. This is the point design. Again, not too much to talk about here, except that we're hoping to get a fusion gain of 2 to 10 and make up to a little more than 100 megawatts of fusion power, which is really a considerable, if you're in that neighborhood, you're really in the energy game. Let me not talk about that, just except to say that we're not trying to innovate on the physics side. We're trying to follow well-established physics precedent from all those experiments that were done. And that's also true for the technology. We want to leverage as much mature technology as possible. The exception being the magnets. In that area we're innovating. Otherwise, we look for precedents from other machines and other industries so that we have more confidence that things will work. This is a picture of the site. So you have, as I said, the control room, offices, and manufacturing facility that's occupied now, has cars parked in front of it instead of trucks. The tokamak hall in the center there, that's 100 feet by 100 feet floor plan to give you some idea of the scale. And then it's surrounded by buildings that contain power supplies, heating sources, cryogenics plant, and utilities. And it's closed in, and it's nearing completion and ready for occupancy. Just to show you a picture of the magnet, because this is an impressive thing. There's the magnet in front of one of the techs. If it looks like a giant piece of steel, that's what it is. One of the innovations in the magnet, we call it a no insulation magnet. It's not really no insulation, it uses steel as the insulator. Superconductor is so good that the current naturally wants to flow in it. So you can use steel. There's many advantages for that, most important of which is the strength, because the forces are enormous. And that winding pack then fits into a into a case of very, very high strength nitronic steel. 1/10 of a millimeter. Yeah. We stack it up, obviously, but the tape itself is mostly steel. It's only 1% superconductor. So the amount of superconductor in there is minuscule. It's almost all steel. Okay, so summary. So the success on the magnet research it's opened up a compelling path, we think, for smaller, faster, cheaper fusion development. We proved out the magnet technology in less than 3 years. The doubters said, yeah, you can probably do that in 10 or 20 years. We did it in 3. Our aim is to demonstrate the first controlled net energy fusion experiment that'll start operation at the end of 25. And then we're targeting fusion on the grid in the early 2030s. And that's very audacious, but it's what you kind of have to do if you want to meet those schedules. It's, you know, maybe this audience doesn't have to be sold on this, but, you know, most of the research has been done funded by governments up until now. So what's the relationship to the government program? Well, we're building on those foundations, decades of patient work. It indicates the value of fusion research, which should strengthen the public fusion program. And it has. For the first time, the government has asked for the Congress for more than $1 billion funding for fusion after sort of years of stagnation. So they've sort of heard this news too. And you build an industry, an ecosystem, like you do with other, like with space, private space endeavors, aerospace, semiconductors. You need a whole ecosystem, which includes publicly funded basic research, universities, and industry working together. And I think that's it.
There any Q&A? I got a microphone for the Zoom people.
Sure.
Peter Dupre, loan 86.
Sure.
Is there any value? I mean, I guess fission occurs in nature to some extent. Does having an insight into that relate to fusion occurring in nature at all?
Not really. I mean, I haven't thought about that. You know, there are examples of where deposits of uranium, I think, have undergone some fission. I think that's what you're talking about. But no, not. It's really fusion occurs in cores of stars, so it's really not something that we have any experience with unless we build these machines.
There aren't any big atoms.
No.
Or big elements anywhere near those stars.
Oh. Well, I'm not quite sure you're saying. Those heavy elements like uranium are made in supernovas, so they're made there, but then they drift, they form into planets. We mine them and then make fission plants. So it's kind of a different.
Thank you very much. That was an excellent presentation. I wanted to ask if there are other alternative, lower energy nuclear fusion possibilities.
Yeah, people have looked at that. There's probably nothing to that. I mean, there's no, the basic nuclear physics is fairly well understood. There have been a few ideas, some of them crazier than others, but that there might be ways of, for example, you can use atoms where instead of electrons, you use muons. If you had a source of muons, that might work, but making the muons costs more in energy. Some of the other ideas really just aren't physics, the physics isn't really correct. Excuse me? People have looked at that. Again, the basic problem you have is that all of the normal processes that we're used to, the forces come from electrostatic forces, bonds. And those characteristic energies are a few EV. And here we need 100 keV kind of energy. So you can never get the kind of, you're just in the wrong neighborhood to get those kind of processes going. So I think if we're going to do this, we're going to do it by making matter really, really hot. I don't think there's any other way that'll work.
What's your biggest challenge?
Well, I think the biggest challenge right now to continue down this roadmap is execution. That is, we think that the underlying physics is sound. We think the technology will work, but it's not easy, right? You know, Ted Williams batted 400, right? So it's done, right? It's a thing you can do, but that execution is not easy. And I think we're in the same ballpark. We've got a potential solution here with no fun. The laws of nature don't stop us, but that doesn't mean it's easy. That doesn't mean we're not going to make a mistake. Doesn't mean a vendor isn't going to deliver a component that's not the specification. So keeping on top of that in a big project, I think that's the number one issue. Then there are some technology problems that have not yet been solved. That fuel cycle, we have a notion of how to do it, but we haven't demonstrated it yet. And there are some experiments ongoing to try to close that fuel cycle research. And then there's also materials questions. We have some ideas on how to start and how to develop them, but there are some considerable materials challenges. What we're hoping, of course, is that as we're successful, we draw the funding not just to us, but to other people who will spend considerable amounts of effort and money on solving those other problems.
Maybe grab one more all the way across the room.
Keep you on your toes.
So if everything comes to fruition, what do you expect to be the power output of the Spark?
Of Spark, it's spec'd for 140 megawatts. And the limit is really the heating of the magnet. The magnet's cryogenically cooled. We have shielding, but not to keep the whole experiment inexpensive, relatively speaking, for $1 billion experiment. We have a limited amount of shielding. And so if we exceeded 140 megawatts for any considerable amount of time, the heat in the magnet would cause it to not be superconducting anymore. The machine could actually produce 300 or 400 megawatts if we just let it full out. It's interesting with these high field machines, you sort of have to, it's like a team of very energetic horses. You have to hold them back on performance. They want to deliver more power than we can engineer for. The next machine would be 500 megawatts, perhaps, something like that. And it would have the proper shielding you needed for protecting the magnet.
Just to calibrate, it's about half the
Yeah. Right. Yes. Very high energy density. And that's one feature of these machines.
So, fascinating talk. So given that your goal is not really, like 500 megawatts is commercial fission, right? 150 is more like naval nuclear power fission. So you've done size versus, energy, but what about dollar per megawatt compared to fission? Have you projected that for complexity?
Yeah, that's a really good question. Of course, the investors ask that. It's of course hard to know until you really deploy a technology what the real costs are. But there is a group at the company that is, experts in future costing estimates. They think it's plausible. Certain things have to break right. And one nice thing about fusion is because the energy density is so high, the basic cost of the materials, if you took a 500 megawatt fusion plant and say, what is the cost of materials there? It's $20 million. I mean, the raw materials. I don't mean the finished materials. I mean, steel, concrete.
Yeah.
It takes a lot of money to turn, raw steel into finished products, but that always sets the floor, and that floor is very low. So the question is how simple can you make the machine, and can you make these machines, say, in a factory and ship them to the site as opposed to building them on site? And that's one of the advantages of going small, is that one of the desirable features of any system like this would be every component could be manufactured in the factory and shipped, as opposed to having to be fabricated on site, because that really pushes costs up. Sure.
And then one follow-on question,
Oh, sure.
for your cycle, lithium is obviously key. And with lithium batteries, we've seen lithium is not all that common on the earth at scale, right?
Yeah.
So is that an issue in your cycle?
Not really. We can outbid anybody for lithium. Yeah. Again, an ounce of the stuff is all the energy you need for your lifetime. So you know. Yeah.
Physical dimension?
Oh, well, this machine, what we call the major radius, which is about 1.8 meters. So from here to here would be, say, 4 meters, 25, 26 feet.
That's a normal size person.
That's a regular sized person there.
We'll go two more. I don't want to take people's night away.
Just a quick question about the fuel cycle. You mentioned lithium, and earlier you mentioned tritium. Is this something that is, I mean, you mentioned it was fairly uncommon, and
Yeah.
where is this a problem that you?
Well, it is one of the problems you have to solve. You need to breed the tritium by utilizing the neutron from the fusion to breed more tritium. And again, that basic process is known. Engineering it into a practical device has never been demonstrated. And so,
And one last one.
okay.
We're gonna wrap up.
The number of years to build, operate, and decommission the machine, I mean, one of the slides says it's about 4 or 5 years.
Right.
And why only 4 or 5 years for operation? Is that wear and tear, or?
No, it's really a question of that the private company, the investors wanting to move on to the next one.
Bigger one.
Yeah, bigger one, a top pilot plant. Yeah. That's the idea is, and it's possible that there could be external funding which would allow it to be exploited further. We're talking about that, but we think we would be ready to build the next machine, and then it just becomes a historic artifact rather than an ongoing device.
Yeah, I don't want to keep people here till midnight, because we're a lot of inquisitive, curious people who will be asking questions all night long. So thank you, Martin. This is our STEM with MIT from Wine Glass
Okay.
learning gift. So enjoy those
Okay, very good.
in your
Thank you.
travels. And again, thanks so much for coming.
Well, thanks for the invitation.